This is AP Calculus BC, and in this video, I'm going to talk about section 9.7, Maclaurin and Taylor polynomials. So this is the point in this series unit where we finally get to actually write out a series that will model a function. And so that's really what our focus is going to be today. Now, the big thing here is when we go through this today, it's primarily just going to be a formula, and we're just going to talk about how to write the series. But I want to talk a little bit about where this comes from, and you'll see as we go through the next couple of sections, you'll start to see how everything we've been doing up to this point with all of this convergence and divergence of a series, it's all going to fit into this idea of writing out a Maclaurin or a Taylor polynomial to model a function. So to start with here, let's start with what we call a Maclaurin series. And a Maclaurin series is actually a special case of what we call a Taylor series. And we'll talk about a Taylor series in a few minutes. But when we say we want to write a Maclaurin series, essentially what we're doing is we're writing a series that has a center point at x is equal to 0. And when I say a center point, if you think back to our tangent line approximations when we were doing linear approximations way back early in the first semester, when we did those tangent line approximations, we would have a point of tangency. Well, that point of tangency was essentially the center point of the model. And I talked about that idea of a center point back in that section because when we get here, the idea of a center point becomes much more important to us. So getting back to the idea of a Maclaurin series, having a center point at 0 means that obviously we've got a perfect model at x is equal to 0. Because what we're going to do is we're going to look at the derivative of our function at 0, and then we're also going to look at higher order derivatives, second derivative, third derivative, fourth derivative, and so on, to get a more accurate model to represent the function that we're trying to model. Okay, so just to give you an example over here, I've got this graph over here that kind of gives you a feel for what we're doing. So we're trying to model the function e to the x. And looking at the graph of e to the x, you can see that we've got this 0-degree polynomial, which is kind of useless. But if I look at a first-degree polynomial, that means essentially doing a linear approximation. So we can see we've got this point of tangency at the point 0, 1. And you can see that that line deviates away from the actual function fairly quickly. So now we're going to use that same idea, and we're going to look at higher order polynomials. So using that same idea of looking at the slope of the tangent, so we can do the same thing with the second derivative, and now we can create a quadratic representation of this function. And you can see that's what this p with the subscript 2, that means a second order polynomial. So our second order polynomial is now starting to have the same kind of curve that an exponential function has, but you can see it's still not increasing as fast as my e to the x curve is. So we can keep getting higher and higher degrees. Here's a third degree polynomial, and you can see now we're starting to get closer to what e to the x looks like. And the higher degree that we get, the more accurate this model is going to become. And so it all is based on that same general idea of writing a tangent line approximation, getting the slope at the point of tangency, getting the function value at that point of tangency, and then writing the equation of a line. Then we'll do it with a quadratic or a cubic or a quartic function and so on. So what we're going to do here is we're going to look at this, and we're just going to write a general polynomial that can be any degree. Now, the process for this is a little bit tedious. We are required to take a bunch of derivatives here. So sometimes the derivatives are very easy, but sometimes this process can take a little bit of time. And the big thing that you have to be careful about is that you can't make a mistake when you're taking your derivatives. Because let's say, for example, I make a mistake on my first derivative. Well, I'm going to take a bunch of successive derivatives. So if I get to my fifth derivative and I made a mistake on my first derivative, that means every derivative after that was incorrect as well. So we have to be really careful. Okay, so I'm going to start with a really, really easy one here. It says, write the Maclaurin polynomial for e to the x. So the process for this is pretty simple, but a little bit tedious. Okay, so my function is e to the x. And remember, if we're going to write a model for this, we need to know the function value at our point. So f of 0 is equal to 1. And I know I'm using 0 as the center point because it says Maclaurin polynomial. Now we're going to take the derivative here. Now this is an easy function to start with, right? It's very difficult to mess up our derivative because the derivative is the same every time. So f prime at 0 is equal to 1. We can keep going with this. F double prime would still be e to the x. F double prime at 0 is also 1. And we can keep going with this. F triple prime is e to the x. F triple prime at 0 is equal to 1, and so on, right? We can go as far with that as we want to. Okay, so usually we go down to a fourth derivative. In this case, I don't really need to, only because the derivatives are the same every time. Okay, so now I'm going to use my formula here. And my formula, remember, it's f of 0 plus f prime at 0 times x plus f double prime at 0 divided by 2 factorial times x squared plus f triple prime at 0 divided by 3 factorial times x cubed, and so on. So the reason that we have these factorials in here in the formula, if you think about when you take the derivative, kind of what happens as I take successive derivatives. When I take the first derivative, I multiplied by 1, right? Because I had x to the first power, I bring down a 1. Now if I take a second derivative, I'm going to bring down a 2, so 2 times 1. If I take a third derivative, I'm going to multiply by 3. 3 times 2 times 1. So that's sort of where those factorials are coming from, if you can think of that in your mind. But notice that the factorial matches up with the degree of the polynomial that we're writing for that term. Okay, so let's plug into this formula. So what we're saying essentially here is that e to the x can be approximated by this formula. And what we're going to use is f of 0, which is 1, plus f prime at 0, which is also 1, times x. So we have plus x plus f double prime at 0 divided by 2 factorial. So that'd be 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus 1 over 4 factorial times x to the 4th, and so on, right? So that pattern will go forever. And in fact, if I were to write all of the terms in this series, not only would this be an approximation, but if I could write all of the terms in this series, this would give me the exact value of e to the x at any point. Now, it's not realistic to use all terms in an infinite series, but we can get an exact approximation by using an nth degree polynomial, indicating that we're taking the polynomial as far as we can possibly go. Okay, so usually when we write these out, we want to write it in a summation form. So what I'm going to do here is now go back to the stuff that we did way back at the beginning of this unit when we were looking at sequences. We were finding patterns in the sequences and we were writing formulas to represent those patterns. Well, here, what I want to figure out is, what's my pattern? So I'm going to write my summation here. I know I'm going to start at n is equal to 0. And I'm going to go from n is 0 to infinity. And then from there, I want to think about, okay, what is actually the pattern here? Well, look at the x's. They're just increasing by a degree of 1 every time. So I know it's x to the n. And then in the denominator, remember 0 factorial is 1. So I had a 0 factorial, I have a 1 factorial, I have a 2 factorial, 3 factorial, and so on. So this is just n factorial. So that would be my series that represents e to the x. Now, if we think back to when we were doing things like alternating series error or integral test error, deciding how many terms I actually want to use to model e to the x would be dependent on what I'm going to do with this and how much accuracy I really need. So let's say I'm trying to evaluate e to the negative 2 power. Well, then this function becomes negative 2 to the n over n factorial. And then the accuracy, just go back to the alternating series error, I can figure out how many terms that I need. Okay, so there's a lot of stuff that we're going to add on to this. So right now, all we're focused on is just write these out and then come up with the summation notation. Okay, so let's try another one here. So this is the sine function, and you can see over here, my sine function, we're looking at different degree polynomials again. So you know which one's the sine function here, but as we increase our degree, so we're starting with a degree 1 polynomial, and look at this one. You can see at 0, we can go kind of a little distance away, and we look pretty accurate, right? Well, then let's look at a degree 2 polynomial. So, and I guess we really don't have a degree 2. I'll talk about that in a minute. We'll look at the degree 3 polynomial. So when I look at the degree 3 polynomial, well, now look, we can go a little bit further away. And if we keep increasing that degree, we're getting kind of further and further out from the actual point of tangency there. Okay, so by increasing the degree of the polynomial, I'm going to get a more and more accurate representation of what this polynomial is going to look like. Okay, so let's take a look at how to write this out. All right, so first of all, same process as before. So my function here was sine x. And if I evaluate that at 0, I'm going to get 0. Okay, then I'm going to get my first derivative. F prime of x would be cosine x. If I evaluate the derivative at 0, I'm going to get 1 because cosine of 0 is 1. Then I'm going to get my second derivative. Well, the derivative of cosine is negative sine, and that second derivative at 0 is equal to 0 again. When I look at my third derivative, the derivative of negative sine would be negative cosine x. When I evaluate that third derivative at 0, I'm going to get negative 1. Then I've got my fourth derivative. Now, the derivatives, we're going to end up taking some pretty high order derivatives here. Once we get past the third derivative, we haven't done this a lot, but we'll do it a lot here. Once we get past the third derivative, I don't want you to keep using primes. It's not very practical at that point to write it or to read it. So we'll start using the notation where in parentheses we'll write what derivative we're taking. So this is the fourth derivative. It would be sine x. And the fourth derivative evaluated at 0 would be 0. And then the fifth derivative is cosine x. And that fifth derivative at 0 is then 1 again. Now notice I went all the way to a fifth derivative. The reason that I took more derivatives this time is because I see these 0 terms. That means there's going to be terms in my polynomial that are going to become 0 terms. And I need to get enough terms written out that I can see my pattern. So sometimes you're only going to have to take maybe 4 derivatives. Sometimes you might have to take 6 or 7 or 8 derivatives to get enough terms that you can identify what the pattern is in your series. Okay, so now let's write the series for this. So for sine x, I can model it with this polynomial. So remember, we need f of 0, which is 0. Then for our first degree term, we're going to need 1 times x. Second degree term is going to be a 0 again. Third degree term is going to give me negative 1 over 3 factorial times x cubed. Fourth degree term is 0 again. Fifth degree term, I'm going to get 1 over 5 factorial times x to the fifth, and so on. Okay, so now that I've gotten it all written out, you can kind of see that there's a pattern here. There's a bunch of terms that went away, and I'm going to write this without those extra terms just to make this a little more obvious. So I have x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the fifth, and so on. And I can kind of see here, based on the pattern that I know shows up within, taking the derivative of sine over and over and over again, I know there's going to be an alternating pattern to this, because what we did before is just going to keep repeating over and over and over again. Okay, so let's now write this as a summation. I've got enough terms. I feel pretty confident about seeing the pattern. So I have to decide what I'm going to use for my counter, so my index. And since I eliminated a bunch of terms, I would prefer to start at n is 0 or n is 1. So typically we're going to start at n is 0, and here I'm going to start at n is 0. So remember, we're no longer referring to the term numbers like we were before, like this being term 1, this being term 2. I'm now going all the way back and I'm saying, okay, let's just look at this without the zeros in it. I'm going to call the x term my 0 term. So I know this is an alternating series, so I'm going to say negative 1 to the n power. That would make the first term positive, right? That would make the n equals 0 term positive. And then I need x raised to some power. Well, I can see that the exponent is increasing by 2 every time. So I'm going to make it 2n plus 1 because when I plug in n is 0, I need the first term to be x to the first power. And then I'm going to divide by the same pattern. The nice thing is once I figure out the pattern for the exponents, I know the pattern for the factorials will be the same because those always match up. So this will be 2n plus 1 factorial. And now what I have is an infinite series that represents the sine function. Okay, and the nice thing about this is if I needed to now evaluate the sine function anywhere away from 0, like let's say a non-unit circle value. Let's say I needed sine of 0.1. Well, I can use now a polynomial to model the sine of 0.1, and I really don't have to use a lot of terms to model that. I might only need 3, maybe 4 terms in that series, and I can get really, really accurate results. You know, we're talking out to the 4th, 5th decimal place. So it's a very, very easy way to model these polynomials very accurately. And then we'll eventually get into the idea of then we can start thinking about derivatives and integrals of the sine function. And rather than working from the sine function, we can work from the series. So we'll see that down the road. Okay, so let's try another one of these. I want you to try one of these on your own. So it says, write a series to model this function y equals 1 over 1 minus x, centered at x is equal to 0. So what I want you to do is pause the video, take a little bit of time, take the derivatives, evaluate the derivatives at your center point of 0, and then write out your series and try to come up with the summation notation. Now, when you do this, don't forget, be very, very careful with the derivatives, because if you make a mistake with any derivative there, every derivative after that is going to be incorrect, and that's going to make all your work that happens from that point on be incorrect. So you've got to be, you know, not rushing through the process of taking the derivative. Be really careful, make sure you account for the chain rule. So pause the video. When you come back, I'll show you the solution. Okay, so here's what you should have come up with. You can see that I started with my 1 over 1 minus x. I evaluated at 0. Then I took my first derivative. Now, when I take the first derivative, I'm going to have a -1 power, right? So essentially I have 1 minus x to the -1 power on that original term. So when I do my power rule, I'm going to have -1 minus x to the -2 power times -1 because I've got to do the chain rule. So every time, even though I've got that negative showing up from the exponent, there's another negative showing up from the chain rule that is then essentially multiplying to make a positive into each one of these terms. So every term turns out to be positive. And when I start writing these out, you can see that then I've got my values here. You'll get to the point that you start recognizing when things are factorials. And what you see here is we've got 1 plus 1 over 1 factorial plus 2 over 2 factorial plus 6 over 3 factorial. Well, eventually you'll see that you will recognize that 6 is 3 factorial. You'll recognize that 24 is 4 factorial. We're going to use factorials a lot. So it turns out that all these constant values essentially cancel out, and I just have 1 plus x squared plus x cubed plus x to the 4th and so on, and that just simplifies down to x to the n. So I've got from n is 0 to infinity the summation of x to the n. Now, interestingly about this one, this is kind of a special case. Looking at that series, my common ratio here would be x, right? So if I had a common ratio of x, let's say we said absolute value of x is less than 1, then the sum of a series that was geometric with a common ratio of x would be the first term, which in our case is 1, over 1 minus that common ratio. So notice that we actually know here that 1 over 1 minus x can be represented by that power series just by the fact that it's geometric. So this one's actually kind of a special case. We really don't have to go through all this process if we recognize that we're looking at a geometric series. So kind of an interesting side note that a lot of these things are connected together, and there are ways that we can shortcut some of these things sometimes if we recognize the patterns that we see. Okay, so let's take a look at a couple more ideas here. So the next thing that I want to look at is the idea of a Taylor series. So we've already been doing Taylor series. So when we do a Maclaurin series, I mentioned at the beginning that a Maclaurin series is a special case of the Taylor series. So with a Taylor series, the difference between Taylor series and Maclaurin series is that Taylor series, the center point can be anywhere. So we can say the center point is 0, 1, 2, -4, 1.678, whatever we want the center point to be, we can make the center point. When we say Maclaurin series, the center point is fixed at x is 0. So this is the general form, and then Maclaurin series is a special case of the Taylor series. But you'll notice here, when you see the formula for a Taylor series, everything here is the same, except for we're always referencing that center point. So we have x minus x naught every time in these polynomial expressions. So if you think back to when we were doing tangent line approximations, that's the same thing we would have done with a tangent line, now expanded out to a quadratic or a cubic or a quartic or however far we go with this. So it's still the same idea, except now we're referencing the center point. It's not 0 anymore. So here's an example of where we would need to use a Taylor series. It says find a series expansion for f of x equals natural log of x about x is equal to 1. So let's just go through this one quickly here. Hopefully you're kind of understanding this process now and you're seeing how it works. It's not difficult, but it's a lot of steps. Okay, so we're looking at our function being natural log of x. If I evaluate this function at 1, I'm going to end up with 0. Now, notice we couldn't evaluate the function at 0, right? Because natural log of 0 is undefined. So we can't have a center point of 0 this time. If I take my derivative, I'm going to get 1 over x, evaluate that derivative at 1, and I'm going to get 1. Take my derivative again. Second derivative would be -1 over x squared. And that derivative at 1 would give me -1. Okay, then we'll go to the third derivative. That would give me +2 over x cubed. And if I evaluate that third derivative at 1, that's going to give me 2. And then I'll go to the fourth derivative. That should be enough terms for us to identify this. So the fourth derivative would be -6 over x to the fourth. And when I see that fourth derivative at 1, I can see it's -6. So one of the ways you can know where to stop is if you're looking at those values that you're getting for the derivative, if you start to see that there's a pattern to them. Like, for example, I'm seeing that these are alternating. I'm also seeing what looks like a factorial pattern. And now that I think I've got a pattern to this, I'm going to stop. If you feel like you need one more just to verify what you think, you can always go further than that. It's really a matter of your comfort level and your ability to identify these patterns. All right, so let's write out our series. So the only difference here is we've got to make sure we account for the center point. So our first term is going to be 0 plus 1 over 1 factorial, which is just going to be, and I'll write it this way so we can see it, 1 over 1 factorial times x minus the center point, x minus 1. Okay, now our next term is negative. So we're going to have 1 over 2 factorial. And we have x minus 1 squared. Then we have plus 2 over 3 factorial times x minus 1 cubed. And then our next term is going to be minus 6 over 4 factorial times x minus 1 to the fourth, and so on, right? So that's our pattern. Okay, so now using that pattern, I want to figure out, okay, how am I going to simplify this whole thing out? Well, before I mess around with this, sometimes it's easier, since I already see factorial patterns in the numerator and the denominator, I'm going to write this out in sort of an unsimplified form, and then I'll simplify the pattern that I see. So I'm going to start it in as 1 this time, and I'll explain why here in a second. Okay, so we're going to go from 1 to infinity, and we've got -1 raised to the n plus 1 power. And the reason I did the n is 1 this time, so remember if I did n is 0, I'm going to get 0. But also, I wanted to be able to reference this n minus 1 factorial that I had there. If I had started at n is 0, it wouldn't make sense to have a -1 factorial, right? So since I left it in an unsimplified form, it probably makes more sense to do it this way. So that would be divided by n factorial. Then I have x minus 1 raised to the n power. Okay, so then from there, I'm going to simplify a little bit further. And I've got an n minus 1 factorial and an n factorial. So in the denominator, we saw this a little bit when we were doing the ratio test. I can cancel out these factorials. If I factor an n out of the denominator factorial and make it n times n minus 1 factorial, then the factorials will cancel, and I'll end up with negative 1 to the n plus 1 times x minus 1 to the n all over n. So now I've got a series that represents the natural log of x. Now, once I've got it written this way, if I really wanted to, I could make my index start at 0 and kind of rewrite the series. There's really no reason to do that unless you really want to, as long as you understand when you're looking at two equivalent series. So at that point, that's my series for the natural log of x. Okay, so again, now if I need to know what's the natural log of, let's say, natural log of 1.2, well, now I have a way to evaluate that, right? My calculator obviously has got a way to evaluate these functions built into them, and it works off of a method similar to what we're doing here with using in this case, a series to model that function. Okay, so let's take a look at one more. I'm going to have you try one more of these, and then we're going to talk a little bit about how do we know how accurate these are. Okay, so it says expand f of x equals e to the x as a Taylor series centered at x is equal to 2. So we did e to the x as a Maclaurin series earlier, centered at x is 0. This time I want you to center at x is 2. So pause the video. Derivatives are really easy. Derivatives evaluated at 2 are very easy, but then plug into the formula and try to come up with the summation notation for that. Okay, so here's what you should have ended up with. Every single one of my derivatives and the first function value, they're all going to be e squared. And every term is going to have x minus 2 to some power in it. And once you see that, it's essentially the same thing that we did with e to the x, except we've shifted it over to have a center point at x is 2. So this is what we end up with for that one. I didn't show all of the steps there. Hopefully that was pretty straightforward, taking the derivatives, evaluating all the derivatives and getting e squared, and then plugging into the formula and seeing the pattern. Okay, so that's a lot of what your assignment is going to be. Now, one thing that I want you to make note of, when a problem says write the third degree Taylor polynomial, that means you go up to and including the x cubed term. Or if it says write a fourth degree Maclaurin polynomial, that means you go up to and including the fourth degree term. So just realize that when they're talking about degree, they're not talking about number of terms in the series. They're talking about how high you go with the x exponent. So sometimes they'll say write the first 4 terms. Well, then the degree doesn't matter. Then you're just actually writing out 4 terms. So there's a difference in the way they're going to reference these things. And depending on what they ask you for, that's going to determine how many terms you need to write out. All right, so when we talk about a Lagrange error bound, we're essentially going to treat this as a formula. There's a little bit to this. We'll talk about it a little bit in class. But the main idea for us is it sort of works on the same general premise as an alternating series error, where we're kind of looking at the next term in the series. And what we're saying when we look at a Lagrange error bound, your book calls it the remainder estimation theorem. It's the same thing. What we're doing is we're saying the remainder after our polynomial of n terms. So remember, when we say the remainder, that means essentially if we cut off our series after 5 terms, if we add up terms 6 all the way to infinity, how much did we leave off? That's the remainder. Okay, so what we're saying is the remainder after a certain number of terms has to be less than or equal to m. Now, notice that m is defined as this. The next derivative term in our series evaluated at our center point has to be less than or equal to m. And so what we do is we just figure out, okay, what's the largest that derivative can be? And we're doing the absolute value of that derivative. What's the largest it can be on the interval that we're looking at? And whatever that largest value is, that's what we use as our upper value for the derivative. And then the rest of this just looks like the next term in the series. So think about if you stopped at the nth term in your Taylor series, the next term would be the n plus 1 term. So we're looking at the n plus 1 derivative divided by n plus 1 factorial times x minus x naught to the n plus 1 power. So that formula is really just the next term in the series. The only difference is instead of just using the general derivative at the next term, we're looking at the maximum value of that derivative on the interval that we're looking at. Okay, so we're going to look at an example of this. Now, if this kind of throws you off a little bit at first, we're going to spend a lot of time on error calculations. And in fact, we're going to have a day where we just talk about error calculations. So for now, treat this as a formula, but realize this is going to keep coming back. We're going to keep working on this. But let's just talk about the general idea of this. So we're using the polynomial e to the x to approximate e to 5 decimal place accuracy. So we want the remainder after n terms when we evaluate e to the first power. That's why this is a 1. E to the first power would be e. We want it out to 5 decimal place accuracy. So notice there's 1, 2, 3, 4, 5 decimal places, and then we have a 5 here to account for rounding. Okay, so when I do this, first of all, remember we found this earlier. We know the series for e to the x looks like this, from n is 0 to infinity, and it was x to the n over n factorial. Okay, so that was my series. So if I want the remainder after n terms at my center point, I know the absolute value of that remainder is going to be less than or equal to the maximum value of the next derivative divided by n plus 1 factorial times x to the n plus 1 power. Okay, so I did essentially x minus 0 to the n plus 1 power since my center point was 0. Okay, so now this one's a little different. Normally, when we have to find the maximum value of the next derivative, we would evaluate at our center point of our interval, and we would evaluate at the end point of the interval that we're looking at. So for example here, if we look at the center point, it would be e to the 0 power because our center of our series is 0. So we would look at e to the 0, and then we would look at the end point. Well, the end point would be e to the first power. So let's just go over here over on the side. This is what I consider when I think of my maximum value. I think of the center point. E to the 0 is 1. Okay, the end point is where am I actually evaluating this? E to the first power is e. The problem that I have here is that the maximum value of my derivative is the value that I'm trying to approximate, right? Because we're trying to approximate e to 5 decimal place accuracy. So we're assuming here we don't really know what e is. So I'm just going to say, well, I don't know exactly what e is, but I know that 3 is a little bigger than e. So if I make 3 my maximum value, I know for sure I'm not going to be further off than, whatever the maximum value is. So I'm setting the maximum value a little higher than I know it is. So it makes my error bound definitely contain the value that I'm looking for. Okay, so I'm going to say in this case then, my m value is 3. Okay, so that means my remainder after n terms evaluated at, in this case, we're evaluating at 1, has to be less than or equal to 3 over n plus 1 factorial times 1 to the n plus 1 power. Now, remember when we did this with the alternating series, we would plug this into the calculator and we would say, okay, when does this get to be the size that we want? Well, we need this approximation to be less than or equal to 0.000005, right? And really we need it to be less than that because we're trying to do an error that's within that decimal place. Okay, so now I would just do that on the calculator, just like we did with alternating series error. Figure out how many terms does it take. That would happen when we get to the n equals 9 term. Now the difference here is, since we did n plus 1, we've already accounted for the fact that when we evaluate this, it's actually getting us the 10th term because we used an n plus 1 index. So what that means is if I want e to the first power evaluated to that 5 decimal place accuracy, I'm going to go from n equals 0 to 9, and I'm just going to do 1 over n factorial, because when I simplify x to the n over n factorial, when x is 1, it just gives me 1 to the n, which is 1. Okay, so that then is approximately, if we plug that into the calculator, 2.71828. So that's my approximation of E accurate to 5 decimal places. Okay, so it's a little bit of a process, and like I said, this error calculation, it might throw you off a little bit at first, but we will keep hitting this over and over again. I only showed you one example here. I want you to try it a couple of times on your own. Just realize that this M value, a lot of times that will just be given to you, so you won't have to go through and kind of reason through it. Most of the time, in fact, it will be given to you, but there are going to be times where you're going to have to check, what's my next derivative at the center point? What's my next derivative at the point where we're trying to evaluate the function? Whichever one's the highest, that's the maximum value for that derivative that I'm looking for. Okay, so as you work through these, at the beginning, if you're looking at the formula for Taylor series and Maclaurin series, that's okay. But after you've done 3 or 4 of them, you want to wean yourself off of that. You want to get to the point where you just know the pattern for this, and you don't have to look at the formula every time. And really, if you just work off of the Taylor series setup every time, remember Maclaurin series just means that in this setup here, the x naught is just going to be 0. So if you work off of this and remember it in that form, then just remember that when it's a Maclaurin series, x naught is 0, then you don't have to think of it as 2 separate things. It's really one thing with a special case. Okay, so like I said, when you work through the assignment, wean yourself off of referring to the formula every time. Same thing when you do error calculations. You might need to look at this at the beginning, but after you've done a couple of them, try to wean yourself off of that so you remember what it is.